Hey, Robert, what are you doing today?
Hey, Michael. Hey, welcome back. Yeah, I'm running the RD30 here. Been running it for over an hour here, and everything seemed to be pretty steady, but now things are changing on me. So
What's changing?
I'm kind of shaking my head here. If you guys want to take a look at the Natoli AIM Pro Plus here, this is kind of telling us everything that's going on in the machine.
All right, yeah.
So can you see the screen, Michael?
Yeah, we can see the screen. We see some forces. We see turret speed.
Well, if you take a look at the forces, we're up in the 6 kilonewtons range. We were in the 3 kilonewtons not too long ago. My forces are increasing, but I didn't touch anything.
No press settings you've changed at all?
I have not. Let me show you what's going on here. So the turret speed is 29.5, about 30 RPM. My feeder speed is only 5 RPM, so I'm running the feeder relatively slow, but my feeder is about 50-60% full, so that's good. I don't have any bridging or rat holding going on. But take a look at my compression. You can see the oscilloscope. You got 4 compression peaks. Looks like the second peak's a little higher. No, it's pretty even. So I got pretty consistent forces. Now, if you look at the left here, it gives me my forces per station. Station 2, 4, 6, and 8. My pre-compressions I'm not using. My main compressions.
Down there too, though, ain't you? You're going from 5.9 almost up 7.5 there. Kind of.
Yeah. So let me increase my feeder speed a little bit and see. That'll help my consistency here. Okay, my feeder speed is now running faster. My forces are all above 6 now.
Okay.
It looks more consistent though, no?
Yeah, it does look more consistent. What do we think's going on though? Because you were at 3 kilonewtons. So what's changed? I doubt the TaBlitz are consistently from previous.
Where am I dosing at? I'm at 6.91 millimeter. I was at 6.91 millimeters in the beginning of my run, so I didn't change that. My fill cam is at 8 millimeters, so I'll have a small push out of about 1.1 millimeter, which is very small. But my force,
pretty good.
I'm hitting 7.
You are hitting 7, jumping from 6, low 6 to 7.
At this point, Michael, I bet you my weights are increasing. So let me grab a sample of TaBlitz, and I'm going to weigh these tablets. I'm going to tell you right now that the weights are increasing. So this is a very common issue you'll see in manufacturing where, hey, an hour, 2 hours later, I got a sticking problem. An hour, 2 hours later, a hardness issue. Something's going on inside this hopper and this feeder, and the Micromeritics are changing. And that's what we're talking about today, Michael, Micromeritics.
That's right. Episode 5, guys. We're talking about Micromeritics. We're going to go over different powder properties, pieces of equipment, why they're used, why they're useful, what we should be testing, what we should be looking at. So our last episode, which Robert's kind of presenting here, Randy Young actually went through the densification in the press. So what Robert did, which Robert, you could explain, you let this run for an hour or so, and we believe it's densifying inside the hopper, correct?
Yes, there's something going on there. If you remember what Randy talked about last episode 4, densifying in the feeder. So what I want to do here is I'm going to grab a weigh boat, and I'm going to pull a sample powder out of this feeder. So let me just jog the feeder. All right, pull out a sample powder. Now I grab some powder right out of the feeder. Compare this to the powder before it went to the hopper, see if there's a difference. I'm going to bet you my lunch that it's different. So now let's go over here to the Micromeritics table.
All right.
So this is the Micromeritics table. Here. Yeah, this is most of the equipment. It's not all of it, but this is basic stuff that you're going to need to measure the Micromeritics, the study of small particles. So I have an oversized graduated cylinder here to show you how we measure bulk density. So here's where we pour our mass into the graduated cylinder and measure the volume. Mass over volume is your bulk density. And we all know bulk density is important to us, right? We like to be above, 0.2, 0.25 grams per ml. Anything lower than that is kind of a light, fluffy powder that doesn't flow well. Causes other problems as well. Tablet design, tablet weight, size.
So when it comes to bulk and fat density, which is what you're going to run here, What are the core things we're looking for when we're running this test?
Well, when we run the tap density tester, hold your ears here.
Yeah, it's quite loud. You see the box. The box is totally scientific screen.
Yeah, the box is here to prevent the loud noise, or you got to put the headphones on. But what we're doing here, Michael, is we are tapping this graduated cylinder to consolidate and reduce the volume of that bulk density material. And we want to measure how it reduces in volume. That ratio is called the Hausner ratio or the compressibility index. And that's how we measure the flowability. That's a very basic way of understanding how the powder is going to flow.
Okay. What do we got up next?
Well, what we have next here is our LOD. You know what LOD stands for? Loss on drying. That's for measuring moisture.
So is that the only method of measuring moisture?
No, you can also use Carl Fisher. So Carl Fisher is a more accurate, especially at the low level moisture content, and it measures the bound water on the crystal structure as well. So that's the most accurate way of measuring that moisture. But loss on drying, basically you put your material on a balance and then it heats it up to a certain temperature and burns off the moisture and measures the resulting weight, and that gives us our loss on drying. That is more important. That's important to us for physical properties. So we're looking at mechanical tablet failures, flow issues, things like that. That is useful for measuring moisture for tablet defects. For example, like lactose monohydrate, it's got water inbound. It's bound to the crystal structure. You can measure that with the Carl Fisher. So that's really where Carl Fisher's used is, getting the most accurate moisture, where LODs used and benefited from looking at physical defects, some flow issues, or it's too dry causing capping issues. This is where your moisture can move around the tablet, causing stability issues, things like that. So we use LOD when we're looking at mechanical failure, tablet defects like that.
So for most of our use cases, Robert, what you're saying is this is adequate enough, the LOD test is adequate enough to devolve into most issues that we're going to face. Not necessarily all, but most.
Yeah, definitely.
Okay. What's up next?
Well, we've got our PSD, particle size distribution tester. We're using a sonic sifter. This machine is actually going to vibrate and pulse, and I get to set the frequency of that. And you pour your powder, excipient formula on top, and you've got these different screen sizes. You got the largest screen on top. Looks like we got a number 30, which is 600 micrometers, all the way down to a 200 mesh, which is 75 micrometers. This is what we call fine particles. Anything below this 75 micron, we call that fines. And excessive fines can cause tablet defects like picking, sticking, capping, compression issues, things like that. That's what might be happening in our feeder. I don't know. But an excessive amount of it's going to cause problems. So again, we got these screens that are put in a machine, pour your formula on there, turn the machine on, and it separates the particles in these screens, and you weigh them, and you get a particle size distribution curve.
So how come you don't necessarily just use your D10, D50, D90? Is there an importance at looking at the different ranges?
Yeah, so D10, 50, 90 is good for a quick glance at the formula, but if you want to identify any bimodal curve or trimodal, things like that, you want to look at the PSD curve.
Gotcha. I think it also helps you assess the area distribution as well when you look at the entire curve versus D10, D50, D90.
Correct. Actually, we have some examples to show the audience them.
Okay, all right. Is there another way of part size testing? Is there another
So there's a bunch of different ways, but Malvern with the laser is a very common way of doing it. And we would use that if we're looking at, let's say, sub-microns. So our smallest screen here is 75 micrometers, but if you want to get into that a few micron, 10, 15, 20 microns, we're going to use the Malvern. So yeah, that's a more accurate way of measuring this particle size distribution. But this is a down and dirty, easy way of doing it. Doesn't take much time, not much investment involved. But yeah, Malvern equipment is another way.
Yeah, I think as a side note, both methods don't necessarily deal with particle morphology, whether you're using the laser scatter, right, or going through particle size distribution. The sieve stack, even, if the particle is like a thin, long particle, it could technically fall through one of the screens because its smallest diameter meets one of the screen criteria. So it doesn't necessarily deal with morphology, and neither does laser diffraction. It kind of assumes a cylindrical shape when it comes to the scatter of the rays. So just a side note for everyone.
Yeah. So the next piece of equipment here, Michael, is called our Flodex. This is a very, very useful little apparatus here. We basically have a funnel where you're going to pour your formulation in, and you put your different we call these the dye holes, I guess you call it, in this little chamber here, and let's see how your powder flows through this hole. Okay, we got all different sizes here. We got up to 30 millimeter. Actually, this is a 32, all the way down to a 4 millimeter dye hole here to see if your powder is going to flow through that hole. So that's called the Flodex.
And that's kind of important too, right? Because when you get to smaller tablet sizes, like let's say mini tabs, particle size really impacts what you're trying to do, right? So it kind of prevents you for how small you can go, correct?
Absolutely. So mini tabs is, say you're making a 2 millimeter diameter tablet. You want to make sure that all the particles flow into that diameter. So our rule of thumb is you don't want the particles to be larger than 20% of the dye hole diameter. So 2 millimeter, 20% is 400 micrometers. So if you got powders larger than 400 micrometers, they might not flow into that hole correctly. So we like to be below that.
Okay, so it's big significance when it comes to particle size then for very small tablet making. It's important to note.
Yeah, absolutely. And when you're granulating, dry or wet, and you're milling, that process is very important, especially if you're doing a mini tab. So a 1 millimeter is 200 micrometers. So if you're granulating, you got to be very careful. You might want to use a hammer mill to get the finer particles, because if you're using an oscillation or cone, if you don't have the correct settings, your particles will be too large and they won't fit into your dye hole. So mini tabs, super critical for particle size.
Well, the Flodex, I think, also has another method of testing set up on it, correct?
Yeah, so I can remove this middle chamber, bring down this funnel, and I can do something called angle of repose. So angle of repose is another way of measuring the flowability. So we basically pour our material through this funnel, and as the powder flows down, we're going to measure that diameter, we're going to measure the height, and then we can calculate that angle. And that we call it the angle of repose. The more something has a high angle, as it kind of peaks up, the more cohesive the particles are. That means they're kind of sticking to each other. Something with a high angle like that's not going to flow so well. So if that's something that doesn't peak out and kind of flattens out, that's something that's not very cohesive, and it's going to flow better on your tablet press.
Gotcha.
But it's a trade-off. There's a trade-off. You got cohesiveness that you want for compression, for bonding, but too much cohesiveness prevents the flow. So when it comes to tableting, there's always a balance going on.
So if we kind of did that flow test and our funnel showed that our powder went basically flat, we could potentially assume that it's not going to bond very well.
Or you can assume it's going to flow very well. It doesn't have very high cohesive forces, and it may not bond very well. So there's a lot more other things to consider there. But yeah, your assumption is on the right path. Yeah.
Okay, all right. Now, there's a higher form of powder testing, correct, based upon characterization, which I think you have one of these in your lab as well.
Yeah, this is the FT4 powder rheometer. This is a sophisticated way of measuring flow. You can look at shear energy. It's got a torque sensor. So this is another way, a more advanced way of measuring that cohesiveness, adhesiveness. And we have a new methodology called the sticking index, which we're going to talk about in future episodes. But we use the powder rheometer not just for flow function, but also to help us figure out what steel type has the least amount of adhesion properties. And that's a whole episode we're going to talk about later. But yeah, this is the FT4 powder rheometer. Other companies offer rheometers as well, but yeah, very, very sophisticated, useful data.
Okay, so just for the audience's knowledge, on July 28th, which we'll talk about this at the end of the show, we're actually going to go in depth on the powder rheometer and talk about the different aspects of what to measure. So there'll be plenty more on that.
Right. All right. Let's look at some examples, Michael. I'm going to go back into the other room here.
Okay. Yeah. Okay.
Okay. So you're going to pull up the TaBlitz software. You have some data in there.
We do. So from our last episode, where we created the rat holing, or not out, I shouldn't say last episode. We created the rat holing as well as the bridging. We're going to be looking at those two different formulation blends because we collected the data on them for you. So we're looking at the micromeritics of these. So we have our M compress,
which is dicalcium phosphate, known for its good flow.
And then our Steolus. So here's our material assessments. So this kind of gives you a breakdown of what what this material is telling us, right? What it's talking to us about. And the first thing you'll notice is that we're highlighting the deviations between them. So here immediately you can see, Robert, we have a bulk density on our M compress at 0.79, but on MCC we're at 0.12.
Big difference.
Yeah, I think there's even another degree of problem here because of and not having enough bulk on the MCC from when it comes to dye filling, correct?
Yeah, so the main problem we had here, Michael, is when we blended the two excipients together, because of the difference in bulk density, you didn't get a good homogeneous blend, and also caused flow issues. So the root cause of that blend issue was the difference in the bulk density, really.
Okay, so then that caused our segregation problem, which we see down here, because of where all the particles sit between the MCC being well below 75 micron and the majority of particles of our M compress being above 150 microns, is what you're saying.
Yeah, that's an optimal size for tableting and flowability. So we got a good particle size for the dical, but look at the right, we got some fine material as well.
Yeah, we do have some fine. As you talk about on the M compress, there's a bit of fines as well in here.
Yeah, that's interesting. And I think we're at the bottom of our jar when we grabbed that sample. So maybe that had something to do with the fines. So this should have been tested before we blended it and put it on a tablet press, right?
Yes, it should have. Yep. Because it had been a leading indicator of potential segregation. Something we should have done too, we should have actually pre-blended them and actually test this, because we can have a third sample in here and actually see what it looked like before. But yeah, I agree. There's different aspects here.
What about the MCC? Take a look at that. That's all fines, basically.
Yep. Almost, let's see, 90% is underneath 75 micron.
Yes. So when you mix those two with the 50-50 ratio, you're definitely getting a bimodal distribution. So
a leading tell here is our car index assessment, right? So we have excellent flowability from this powder from testing. Mm-hmm. And then our car index here, we have very, very poor flowability, extremely cohesive. Now, this MCC is not intended for direct compression. I believe this is a dry granulation or wet granulation version, correct?
Or dry or wet. It's a granulation material. You're going to add that in the granulation process. Unless your API is very fine material as well, and you want to blend this material with it, but you're going to live with low bulk density and challenges on the tablet press. But yeah, I would use that grade of MCC for a granulation process.
Okay. So something else to look at here is when you're starting to deal with fine particles, there's actually other issues that could come into this spectrum that you need to look at, and that is sticking. So when you have a significant amount of fines, sticking can happen on your punch face, especially when it comes to engraving. Okay, and that's just a problem that you could potentially have. So looking at particle size distribution ahead of time is good to understand. So you have a good compressible powder, it's homogeneous, and you potentially have less sticking. But also, you can see your flow differences between those because of how different they are in the array of spectrum of which particles they cover for those sizes. And then your distribution. Go ahead.
Explain the color coding right here. We got a lot of reds. Reds are red flags, right?
Yeah, reds are red flags. So when you have a lot of fines, which both of these, there's on the M compress, both of these are about 20% here, 15-20% here of fines, and then you have all fines almost over here. There's significant indicators where you might have a series of issues potentially. Now we didn't collect the moisture content on here, so this is kind of a misnomer. But whenever you do collect the moisture content, that'll actually play into how those fines are going to operate and potentially bond. So we're highlighting basically the risks you want to look at, and the biggest risk here is obviously fines and then particle size distribution. So we do have a better particle size distribution, obviously on the MCC, because all of its particles are basically in the same window, but it's a negative impact because all of them are fines, right? So you don't necessarily want them all to be fines. Whereas on the M compressed, we have a little bit less of a homogeneous particle size distribution, but you still do have some fines, and your area distribution, right, is a pretty big degree here. So your coefficient of variation. So there's different things to balance here when you're looking at particle sizes and their homogeneous between the sizes. So that's kind of what you're breaking down here.
Let's also look at the point of these materials. These are diluents, right? So these diluents, you want the particle sizes to be in a nice sweet spot. The fine materials, it's okay to have some. It kind of fills in the gaps between the larger particles to help bond, but excessive amount of fines prevents that bonding process when you got also large particles involved in there. So the fine particles are usually going to be your lubricants, your disintegrants, maybe your colors, your flavors, I would say glidants. So you're gonna have some fines, but you want to minimize that. So these materials, we're using dicalcium phosphate, M compressed, and microcrystalline cellulose. Those are diluents. You want those particles to be right in your sweet spot. You shouldn't have issues with your tablet because your excipients are at fault here. The API is usually the challenging piece in your formula. Don't make it your excipient. So understanding these basic micromeritics is super important. Choosing the right diluent for your formula, super important. So that's kind of what we're summarizing here. Measure your micromeritics, even as a quality control. Michael, how many times did we see customers call us saying, hey, we're having problems, but we didn't do anything different? Just like I was showing you there in the back lab. Well, what is different? Nothing. What? You change your excipient company. Yeah, but it's still the same material. But let's test the micromeritics. Then we find out that it's actually not the same material. So do your homework, your due diligence. When your raw materials come in, at least measure your bulk density and your tap density just to see if anything right there has changed. If you see a difference there with bulk and tap, now let's look at particle size distribution. Now let's look at moisture. So you're setting yourself up as a nice quality check for your raw materials. You don't have to test everything at once, but you can start small. And if you see an issue, a red flag, okay, now we got to do a little bit more testing. So that's the point of what we're trying to explain here.
Yeah, we kind of went over a little bit of time here, so we're at about 6 minutes here for questions. Let's jump into questions. But while we're into questions, I guess let's dive into that a little bit, Robert, while we're waiting on questions to come in. You were saying, having that balance and material properties from micromeritics, but also material type. I think between fracture materials or elastic materials, you kind of have a balance of all those things that you're trying to do when you're looking at basics of formulation, correct?
Yeah, absolutely. So when we get to compression in this whole podcast here, we're going to talk about how materials deform. So when we actually apply a pressure to these particles, these powder particles, the way they deform is important to us as scientists and formulators. Like MCC, microcrystalline cellulose, is a plastically deforming material, which means when you compress this material, it elongates, stretches, and increases surface area for more contact area. That's what gives you strong compacts. But like your dicalcium phosphate M compressed, that's more of a brittle fracture material. So they fracture into smaller pieces. You're not going to make as hard of a tablet or strong, but you're going to have less speed sensitivity, less sensitivity to lubrication, and so on. Looks like we have a question, Michael.
We do have a question. So how was the particle size distribution measured? And I'm assuming it was from the results that we had from episode 2. So you used the sieve stack in there that you actually just showed us, correct?
That is correct. So basically, we use the sonic sifter. These are larger screens, but we use 3-inch screens of different sizes, up from 680 micrometers down to 75 micrometers, and a bunch of screens in between. And then we basically shake the material, and it separates them into the different screen sizes, and then we measure them, and we get the particle size distribution that way.
Yeah, and just as a side note, you can do that same measurement with larger particles for laser diffraction, but you don't necessarily need a Malvern to measure these. You can absolutely use a sieve stack. Malvern can do larger particles though as well.
Right. Yeah, thank you for the question.
Yeah, absolutely. And then for those of you on LinkedIn, all right, if you message in the chat there on the event, your questions will show up here. And for those of you on YouTube, you use the super chats on YouTube, and then they'll actually pop in here, and we can answer your questions. Okay,
how much time do we have, Mike?
We have about 3 minutes. So while we're waiting on the next question to come in, I did want to bring up the next episode. We want to make sure we cover what our content is going to be here. So we're going to go over the FT4, and then in that, we're going to touch some highlights. I think we're going to go over the Moore circle and a couple other things. Robert, what are we covering?
Yeah, we're going to even touch on the sticking index if we have time. So we look at the difference between the cohesiveness from the particle interaction to the adhesiveness of the particle to the steel type interaction. So we use a torque sensor to measure shear forces and energy to give us that sticking index. So there's a bunch of things we're going to look at with the powder rheometer.
Okay, yeah, and we'll actually even look at a flow function, I believe, as well, to help determine how well your powder flows, and then the scale in which you can devolve or derive that flowability of your powder from a more sophisticated measurement system. So today we looked at things like the angle of repose, right? And that is one methodology, as well as the car index, but this is a more sophisticated way of measuring how that flow is going to take place in your press.
Correct.
When is the next episode scheduled regarding the sticking index? So we're actually probably going to do a 2-part. So we'll touch on it next episode, which is July 28th. So same time as usual. It'll be July 28th, TaBlitz Tuesdays. And then we'll probably have a touch point on it, and then we're going to go fully into it, I would say, in a couple of weeks after that. So we'll announce it next episode when we'll cover that.
Yeah, Michael, the sticking index might be more in a couple of weeks because we're going through all these steps. So if you want to reach out directly to us because you're having a sticking problem, you can do that. We're here to offer support after this podcast webinar here. So please reach out to us here. You can see the Dr. TaBlitz there. If you're having a sticking problem, we can describe to you the sticking index on a one-to-one basis and fix your problems right away. Sticking is probably the most common issue we see across the board with tableting. So please don't wait until the episode. If you have a question, reach out to us, email us, give us a call. We're here to help you guys.
Yep. Yeah, the second most difficult task I think that we get mentioned, from powder obviously flowing into the die being the first one. Then they did all that effort to get their powder there, only for it to have sticking issues on the punch, which we should clarify, right? Sticking issues and ejection issues are different. Sticking is usually associated to the punch face, right? Or sticking to, the powder sticking to your mechanical components physically being stuck there, not necessarily high ejection forces. So we have a lot of people who do confuse those. Robert, you can probably speak more to that here. We're actually have time, but please, if you need anything to add.
Yeah. So how much time do we have, Michael?
It's 10:30 on the nose. So we're actually at time here.
All right. Well, until next time, 2 weeks from now, we'll see you again. But again, you can reach out to us before that with any questions. Again, ejection, sticking, flow, micromeritics, any tableting compression issues. We're here to help you guys.
Yep. So episode 6 will be on the 28th, same time at 10 a.m. Eastern time. So we will see you there. Thank you, everyone, for joining. We appreciate your time, and keep following Dr. TaBlitz.
Great. Thank you, everybody. Good seeing you.